being back in Cambridge has brought back a lot of nostalgia. I'll tell another story. A few months before the 2017, the first Big Proof conference, Rob Lewis and Johannes Holzel came up to me and they asked me, to suggest, what would be a really, if they were going to start a really great formalization project, what should they do? And I answered right away. I said, well, you should formalize Maryna Viazovska's results on sphere packing. I had no sense of how hard or how long, but I just thought that would be just a great formalization project. And Tom Hales is a colleague in Pittsburgh, and we discussed it with him. And if you actually go back and watch his video from the Big Proof meeting, he mentioned that as kind of a flagship, as a formalization project that someone should do. And so I'm pleased to say that people are now doing it, and Maryna will tell us about that. So, Maryna.
Yes, thank you very much for the introduction. So, yes, let me tell you my story of how I embarked on this project. So a couple of years ago, EPFL invited Kevin Buzzard to give a colloquium talk, and he gave a colloquium talk about formalization, and it looked like a very interesting talk, so I wanted to try to somehow learn more about formalization, and I heard from people that a nice way to learn about formalization, trying to formalize something. And so yeah, so I thought, okay, let's formalize this. So also, I tried to play a little bit with Lean. I realized that there is no way I could do it myself. So I think the last previous talk was about experience of a mathematician with Lean, and I realized that I will not be able to doing it without help of other people. And I thought, if I need the help of other people, then maybe the project needs to be something exciting. And so yeah, so I decided to do this. At this point, I also had no idea of how feasible this would be, how difficult this would be, how long this would take. But I was very fortunate to find other people who want to work with me. And yeah, so now it's a joint work with Christopher, Sid, Gareth, Bavik, Shivu, who already actively contributed to the project, and also a big number of people who gave us all kind of technical support, moral support, did things we could like told us, like shared their experience, their expertise. Yeah, so so maybe one thing I want to tell you that so like one person with whom I worked particularly closely was Siddharth, and it turned out that at the time when Kevin visited the EPFL, also Siddharth was doing his 1 year of master studies abroad at the EPFL. So we had an opportunity to work together and to start with a smaller project, which would be also a part of this bigger formalization effort. But let me start with the mathematics. So what I were talking about, so the sphere packing problem, so what is it about? Yeah, so we have how the sphere packing problem goes is that we have a big container, very big container, and an infinite supply of hard balls of equal size, and we try to put those balls into a container, and somehow we can imagine those, like our container being a ship and balls being cannons, or this could be positions of atoms in condensed body, and even though like, historically this is how people thought about sphere packing problem, and we know this from Kepler's manuscripts. From today's knowledge about condensed matter, we know that, okay, this is a beautiful metaphor, but maybe now we know better. Or we don't need to stay in dimension 3, we go to other dimensions and still find this problem still would be useful, for example, in classical communication theory. And so like the game is that the box is very big, and so the boundary effects make no role, and we only care about the density of this packing. And so this is the formal definition of what is the sphere packing problem. So we will do it with d-dimensional Euclidean space. And so for each dimension d, what we would like to do, the number called the sphere packing constant, which is the biggest density we can achieve in a given dimension. So here I got some visuals. So this is like dimension 1, 2, 3. These are all the dimensions that we are already solved. And so, so these are the upper and lower bounds. So here you can see that, like, among the finite dimensions, we know that the problem is solved in dimensions 1, 2, 3, 8, and 24, and in other dimensions we still have a gap between the best known density and the best known upper bound. And so here one particular bound that is used a lot is based on linear programming ideas, and here I plot the Connell-Elkis bound. So how do we solve this fair packing problem? We need to somehow solve essentially two different problems. One of them to construct a good packing, and another one is to prove an upper bound on a packing density which will coincide with this with the density of a known packing. And so, like, as you can see from this plot, is that the Connell-Elkis bound, it does not work in most dimensions. In most dimensions, it still leaves us a gap. So somehow, of course, like this red line, it's obtained numerically, but I think we have quite a lot of confidence in it that at least by this method, it cannot be improved too much. But so we see that, like, this lower bounds and upper bounds, it seems like if you look at the picture, they coincide in a few points. And so on this picture, we can see that coincide in points 8 and 24, at least numerically. And also what we cannot see that great from my picture, but in fact, they do coincide in dimensions 1 and 2. But then dimensions 1 and 2, we already know, actually, we know easier methods how to prove sphere packing problem in dimensions 1 and 2, so it's not so interesting. And so, yeah, so these dimensions 8 and 24, this is what I'm going to talk about today, is that actually those lines that meet on the plot, they do meet in reality, so that they do intersect and therefore solve the sphere packing problem in dimensions 8 and 24. And so, yeah, so in dimension 8, we have a very nice example, which is an E8 lattice. And so here's one particular realization of E8 lattice as a set of points in Euclidean space. There are other descriptions of it. There are actually many descriptions of it. E8 lattice is like a rock star of mathematics. It appears in all possible places. So, like, another way to describe E8 lattice, it's a unique even unimodular lattice of rank 2. So even it means that all vectors in this lattice, their length is the square root of an even number, and unimodular means that its covolume is 1, and so it is rank 8 is its rank 8 as the rank of a Z module. And so this we know what is the minimal distance between 2 points of the lattice. So if you want to make our to pack with unit balls, so then we have to scale the lattice. But here this is the matter of choice. So we can, like, prove these games in different ways. We can fix the density and then ask for biggest possible radius, or we can fix the radius and search for the best density. So this is the same thing. And so the theorem I will speak about today is this theorem, which tells us that the E8 lattice packing is, in a sense, the best packing in Euclidean space. And so the E8, the packing constant for dimension 8 equals to the density of the E8 lattice. So this would be the result we would like to formalize. And so just to tell you that this story continues, still works in dimension 24, as we have seen from the plot. And this is also something we have proven. So in dimension 24, we have another remarkable point configuration, which is the Leech lattice. And now the Leech lattice, it is also even unimodular lattice, this time of rank 24. And we know that in dimension 24, we can actually 24 different even unimodular lattices up to isomorphism, but only one of them has shortest vector of length 2. Because by the property of being even, the smallest length which is allowed is square root of 2, but among those 24 lattices, this is the only one where the square root of 2 is not realized, and only 2 is realized, which is the next possibility. And it's somehow, this time we don't need to rescale anything. This time, whatever we like to have unit co-volume or unit size of the balls, they actually, everything agrees neatly, and so this is a theorem we proved jointly with Henry Kohn, Abhinav Kumar, Stephen Miller, and Danilo Radchenko, is that so the sphere packing constant in dimension 24 is equal to the density of the Leech lattice. And so our proof, it relies on this result of Kohn-Elkis, and the result of Kohn-Elkis tells us that it gives us this method for proving upper bound. So it's called the linear programming for some historical reasons. So when things are written this way, it's not very clear. But yeah, like one way to think of it is that okay, the space of Schwarz functions is a linear space, and all our relations are convex conditions. So that's why this is where analogy happens. And yeah, so the theorem tells us we can construct this auxiliary function f. An auxiliary function needs to satisfy this. Three conditions, which kind of like maybe first one we can see as like these two conditions, they kind of compete with each other, and the third condition is a normalization. So if we normalize our function so that the value of the function at 0 is the same of the value of its Fourier at 0 is 1, then it would be somehow hard for function, so that we are asking for the function itself to be negative everywhere except of our small ball, and for the Fourier transform to be positive everywhere. And these are conditions as if we're making our radius smaller, and smaller, these conditions become difficult to satisfy. And so once we can find such a function, then we can get this bound on the packing density. And so, yeah, so actually what, so this is a small proof of the theorem. And the proof is, actually, it really relies on the essentially Poisson summation formula. Okay, so here let's prove this for periodic packings. So maybe looking at all packings is complicated, a lot of difficult analysis comes up. So let's just think about periodic packings, and it means that there is some small, like lattice with big co-volume, so that our packing is translation invariant with respect to this lattice, but so again, periodic packing is not the same as lattice packing. This is sometimes some confusions we have with physicists, because for them periodic packing is actually lattice packing, but not for mathematicians. And yes, now we would like to estimate the number of. So if we want to estimate the density of this packing, we would like to estimate the number of lattice points in modulo lambda in any fundamental domain of lambda. And so we are writing this series of inequalities. So we take, so here we are using, at this step we are using the first condition of the Kohn-Elkis theorem. Here we're just like rewriting our formula a little bit. Then we are using Poisson summation formula, and we get some where not the function f, but its Fourier transform is involved. So at this step, this is the step where we are doing some kind of computations. This is maybe actually the rabbit of this theorem. And so now what we can do now, we can use the second condition of Kohn-Elkis theorem. So remember that we know that Fourier transform has non-negative values. And so now we have this inequality which relate our f of 0 and f of 1. And this is where we can remember about our normalization. And then if we compare these two sides of the equation, we will actually get what I've promised you on the previous slide. Because now if you know the covolume of the lattice and number of lattice points per lattice translations, we will be able to compute the density. So now this is how the proof works. And so yeah, so here there is like one question. One thing is that we have proven it. So now we have proven this theorem of Kohn-Elkis, but only for periodic packings. And here there is one more step, which is already like known and in the literature is that actually when you are taking supremum of packing density over all periodic packings, it is the same as taking supremum over all packings. So this is not a very big assumption. So from this proof with that one well-known result, we can get the full power of Kohn-Elkes theorem. And so Kohn-Elkes, they did themselves similar computation. Okay, so I think here I have messed up a little bit. So actually, okay, so this should be referred to the previous slide. So the computation is actually done by Kohn and Elkes. So I apologize for confusion. But the previous theorem, it was discovered by Kohn and Elkes, and independently also by Dmitry Gorbachev around the same time. And I spoke about, I think they did their discoveries independently. And so what Kohn and Elkes did in their paper, they actually applied their theorem, but now to concrete dimensions, did this they constructed numerically these auxiliary functions, and those auxiliary functions, they would not solve the sphere packing problem completely. However, they would give these very close errors that are very, very small. They were considered very small in 2003, and then since 2003 there have been a lot of more computations, and so at a certain point, Henry Kohn, he could have improved this like 3 zeros to, I think, 20 or 60 zeros. So there was like a lot of confidence that this is actually the correct answer. Of course, the only problem is that the magic function was constructed only as approximations. And so, of course, there was a conjecture, what Kohn and Elkes conjecture, that there exists actually a magic function, and the term magic, it was not used in the Kohn-Elkes paper, but I think the term was suggested by Stephen Miller too. Like if we have this auxiliary function which actually solves our problem completely, let's call it a magic function. So, and I think it's a nice terminology. And so the theorem I would like to speak about today, it is this result that there exists in fact a radial Schwarz function as a function of 8-dimensional space, which satisfies all the the best possible conditions of the Kohn-Elkes theorem. So there is a similar theorem we have proven for dimension 24, but this one we have not started formalizing yet. So.
How much more complex is it?
Not okay. So there are maybe it's not much. So many ideas translate directly, but then there are also some interesting phenomena which, like I would say more on the technical side, which come up in dimension 24. So I think in terms of formalizing, there might be quite a bit of work. So there are some kind of new problems that arise as we in dimension 24. So somehow ideologically everything works the same, but then there are new effects. And yeah, so this is the plot of this of the magic function and its Fourier transform, and the magic function. So I guess a few words. So like this is a one-dimensional plot, and I have a function in 8-dimensional space. So maybe so what happens here is that this function, it's a radial function, so its value depends only on the distance to the origin, and so this plot, it gives us the it depicts the value of function as a function depending on the length of the vector. And also, so it's a Schwarz function, so it decays very fast. And if I plot the Schwarz function itself, you would see like a very small bump at the beginning, and then it just would be merged with the x-axis. We would not see some interesting features. And here, some interesting features are these zeros and double zeros. So these are somehow the key to understanding the function, and also somehow a secret way to discover the explicit formula for them. So like another rabbit in here. And yeah, so as I already told you, we can think of our function E8 as being a radial function. So and here it's like if you have some other magic function which is not radial, we just take all its rotations around the origin, and they will satisfy the same conditions, because all the conditions in Kohn-Elkes theorem, they respect rotation with respect to origin, and so then this averaged function would be a radial function, and it will also satisfy the conditions. And working with one-dimensional functions is nicer than working with 8-dimensional, for functions of 8 variables. And so another thing is this explanation for the double zeros. And like one way to see it is that we can come back to that proof which I showed you before, and we plug in our function into the Poisson summation formula for the lattice, for the E8 lattice. And so we know that because we know that here all the inequalities, they have to be equalities. And so the only way all these inequalities can turn into equalities and still the conditions of Cornell-Kiss theorems are satisfied, it happens if and only if this this holds. So we know that then the values of magic function and the values of its Fourier transform, they will be 0 at all square roots of even positive integers. And actually, it turns out that this condition is sufficient to recover the function uniquely. So if you know the function is Schwarz and radial and satisfies these conditions, we can recover it uniquely. So this is what we know now, but this was a bit of a later work. So what we did in 2016 paper, I just like written this explicit formula for E8, because for solving the sphere packing problem, we don't really know that the function is unique. We just need one function, and so this was a function like this, and so this function was constructed in this in this form, which I will explain a bit later. But maybe in this talk it will still stay a little bit of a mystery. Why do we have to search for a function in this way? But here maybe as a just explanation, simply my explanation is that we know that our function has double zero, so this is how we insert this. This factor, and so then we write it in this form because we need to compute the Fourier transform of it, and Fourier transform somehow works nicely with Gaussians. And then somehow a lot of, but then if you really want the second condition, this is when things get interesting, and then when we can actually pinpoint what should be the function phi that we insert in here. Okay, so now there's somehow this function phi. It turns out that it has some hidden symmetries in it. So it would have symmetries of the group SL2Z acting on the upper half plane. So on the previous slide, what we have seen, we have defined our function's integral from 0 to infinity. But now what we have to do, we have to think of this half integral from 0 to infinity as this ray which is imaginary axis embedded into an upper half plane. And then we can extend our function to the whole half plane, and then it will be a very nice symmetrical function. And so here, this is where we would need the theory of modular forms. So it turns out that the symmetries of this function are described by the theory of modular forms, and here is let me introduce you to the zoo of modular forms. So these are the usual holomorphic modular forms. They are functions which satisfy these symmetry conditions on the upper half plane, and they are holomorphic at the upper half plane, and they also have nice behavior as we go to the boundary of the upper half plane. So here's a bit of a technical condition, but I would say that our modular forms, they have to be holomorphic at cusps, not only at the upper half plane, but also at the cusps. And we know a lot about these spaces. We know, for example, that these spaces are finite dimensional, which makes them computable, so we can compute them effectively and work with them. And, for example, compute what would be very important, but also being able to compute their Fourier expansions. And then somehow the zoo of modular forms goes further. We can relax those conditions. For example, we could say, okay, being holomorphic, maybe it's too much to ask. We can allow for some singularities, for example, poles. Sometimes we can allow for poles in the upper half plane, but here we allow only for the poles at the cusps. Also, so this space of modular forms has some interesting inhabitants in there. So if we have defined this space of modular forms abstractly, but now are there any elements actually in this space which are like non-zero, non-trivial? And here is a very classical example, Eisenstein series, so something which we know from the beginning of 19th century. So if we take a double sum like this, we will construct a modular form of weight k, where k is an even integer which is bigger or equal than 4. And we know that this Eisenstein series, they are holomorphic modular form of weight k and level 1. And also we have a nice number theoretic expression for the Fourier coefficients. So these are all classical effects in modular forms. And then another thing which we would need these quasi-holomorphic modular forms. So here the story is that we don't restrict our conditions on holomorphicity, but instead what we will do, we will allow our functions not satisfy the transformation rule perfectly. We will allow for some controlled error term. And so the Eisenstein series E2, they satisfy this somehow slightly more complicated transformation formula. And so objects like this, they're called quasi-modular forms. And they often arise, for example, if we try to differentiate our modular forms in the upper half plane. Or if we try to sum things that don't really sum up. So another. So here again, I'm keep showing you somehow the main characters of my play. So another modular forms that we know for a long time, and we know quite a lot about them, can compute their Fourier coefficients, are this theta series or theta nullwerte. So they are so-called modular forms of weight 1/2. And again, because they have this weight 1/2, they will not really fit with my previous definition. So they are again some special species. But what is a good thing is that the proof of if you want to understand their transformation properties, then what we need to know would be the Poisson summation formula. And yes, here are some more like elliptic J invariant, and also we want to know. This is an example of weakly holomorphic modular form, and we want to be able to compute its Fourier coefficients. Okay, so maybe what I told you, it was about what I showed you now. This is probably in the book, which was 2 lectures before. So if you remember that book, so this is probably where you can find all these definitions. And yeah, so now how can we construct the solution to our problem? So what we need to do, we have to construct 2 modular objects, which, and here I define them. I know that they belong to these 2 spaces, which I defined before, and they need to have this Fourier expansion. And it turns out that these conditions would define my function phi and psi uniquely. And if I have these 2 functions, then I can define my magic function in such a way. And so the theorem that I would like to prove and I would like to formalize is this theorem, that this radial function g, defined in this way, it satisfies all these 3 conditions. And if I can prove them, then I can plug them into Kohn-Elke's theorem and solve the E8 sphere packing problem. And so yeah, so here maybe some important steps of the proof is first I should be able to compute so maybe like there is a 0 step I did not include here, is actually to show that it's a Schwarz function that is indeed well defined. Then I have to compute its Fourier transform, and for example compute in this form. And then I have to check the first 2 conditions of the Kohn-Elke's theorem, and it would come from these 2 steps. So this essentially it reduces to proving these 2 inequalities. And this would prove and if I know that this function under the integration side satisfies the inequality, then of course after I integrate, it still satisfies the inequality. So this would imply the results I had on the previous slide. So it will prove these 2 results. And then I also have to verify these conditions. But these are maybe like 2 somehow 4 important steps, and then we are done. And so now, okay, so this was somehow the like informal mathematics part, and now we have decided to formalize this, and so this is why we have started this project. So now this repository already exists on LinHub, and today our plan is to make it public. So before it was not public because we were still working on a blueprint and working on formalizing some of the important results. Also part of this formalization, it was first a like small summer project, but then also a master project for Sid. But now he had his exam 2 days ago, so now we can open it and make it public. And so this is what we were able to build so far. So this is our current dependency graph. Our current blueprint with which we have to work in, and yeah, so maybe on the blueprint it's a bit difficult to read what is in here. So let me go over different important parts of this blueprint. So this is okay. So here I kind of simplified a little bit. So this is, I would say, a simpler version of the blueprint we have seen on the previous slide. Okay, so what do we need as an input to our theorem? So first we need some basic notions on a sphere packing. So we need to define what is a sphere packing, what is a lattice packing, what is a periodic packing, what is a sphere packing constant, prove several results that people in principle know about sphere packing, but they have not been formalized yet. Then, as you have seen, we also want to use the Kohn-Elkes theorem, and in order to be able to use Kohn-Elkes theorem, we will need some facts from Fourier analysis. So, for example, we need the definition of Schwarz functions. Unfortunately, it is already in the MATLib. Then we need the Poisson summation formula, and the Poisson summation formula does exists for Z, but we need a more general version for any lattice. So this one does not really exist yet. And yeah, and so after we have after these parts and these parts would be done, then, for example, we can formalize the Kohn-Elkes Gorbachev theorem. So now everything is almost everything is ready for it. So the linear programming stands for the formalization of the small proof which I showed you, or the sketch of the proof which I showed you before, of the Kohn-Elkes Gorbachev theorem. And another thing which we need would be a contour integration of holomorphic functions on the upper half plane. And so this seems to be technically, it seems like it's not in Lin yet. So I know that we would need statements like a Cauchy-Gurza theorem. And I know that now it already exists in Isabelle and does not exist in Lin yet. But also, I don't know, I should confess that the Cauchy-Gurza theorem was one of my favorite theorems as an undergraduate. So it would be really great. And I think as a number theorist, I also think it's super powerful. So unlocking that one would be really great. And then we needed so many different facts on modular forms. And fortunately, Lin already has a library on linear forms, so many things are already defined there, or certain facts are proven. But now we need to have these modular forms, but with more computational angle, because we want to be able to take modular forms to compute their Fourier expansions, manipulate with their Fourier expansions, prove their transformation properties, and so on. So I will also speak about some of our frustrations in this respect. And then after we have all this done, but we can proceed to the construction of the magic function. So then this was the main topic of Sid's thesis, right, Sid? So there was actually to make the formalization work in here, to formalize all the key statements from the construction of the magic function. And so, when there is the magic function is constructed, we can prove those three, like the inequalities we can now fulfill these steps like 2, 3, and 4 from my previous slides to prove to. And so here there is like in my actually initial proof, this was a bit of I don't know how to say shady area because so I had this like 2 very explicit functions which I told you I was able to compute their Fourier transforms to many like to any length, and I could just plot it. So it's like 2 functions of 1 variable, like defined on a half line, and I can just see, okay, so this one is positive and this one is negative, and I could compute somehow how the asymptotic behavior near 0, like near the endpoints near 0 and near infinity, and there also everything looked like asymptotically positive. But then in the middle, okay, so there is this truncation of the Fourier Fourier expansion, and so it already becomes like essentially not like an exponential polynomial mixture of exponentials and just polynomials, and proving that that is positive is like very boring tasks. So yeah, so like one can do this kind of like interval arithmetic to I don't know to estimate the error, and then to so if we were like much more for in the 24 paper we have actually did it by we found like some polynomial, proved that it's positive by what's called the Sturm's method, and then somehow proved also rigorous estimates on all error terms. But it was already like in this semi-formal way. It was very painful to do that, and formalizing that in lines should be super painful. So it seems like it's a very for formalizing that would be an unpleasant thing. But fortunately, a long time has passed since my theorem was put on archive, and so there are actually people who have changed this step. So this is maybe about also our discussion, like, is it good to formalize problems, theorems as we write them, or is it good to wait? I don't have an answer to that question, but maybe both somehow approaches have their merits here. Because now there are actually 2 different formalizations, one by Dan Romnik and another by Sivu Lee, who did this very analytic proofs of the inequalities, which do not really require things like interval arithmetic or the Sturm's method for polynomials. And then once we have all this in place, we can get our final result, the answer to the question, what is the sphere vector constant in dimension 8? And so this is this number, which is the density of the E8 lattice technique. And so, yeah, so now let me somehow dive in more into some of this, the particular things. So this is the sphere packing part, the basics of sphere packing. And so again, so this is something what was done by Seed, Garrett, and Barwick. Mostly, so this is somehow the state of the art. So you can see, unfortunately, like none of this is dark green yet. But also you can see that yeah. Okay, so here somehow okay, so on my computer, like the color coding looks a bit closer to the standard thing which you see in the blueprint. Here, all somehow, yeah, all backgrounds look white, but they're not all white. But so maybe I'll just explain. So, like things in green are essentially things that have been formalized, and maybe their proofs have been formalized, but they still depend on certain things which have not been proven. So things in blue are things that have been the statements have been formalized in Lin, and yeah, so the orange part, it means that even the things have not been exactly formalized yet. And so here maybe like among all the things that we probably would like somebody to jump in are actually like I think like this part is something we have not done, but it seems like an interesting result on its own. So it's yes, like to prove that the so it's so one of these like basic but still interesting results in analysis that if we take supremum of a packing density of all periodic constants, then it will be the same as taking supremum over all packings at all. And so after this is done, this will also complete our. And so another interesting thing, which is so we also as like for the part of sphere packing problem is to prove that we have an example. So we have to convince Celine that we do have an example. So we do have a sphere packing which has exactly this density, which would be to prove that the E8 sphere packing has exactly this density. And so we have made a lot of preparatory work for this, and somehow this was my maybe like actually first experience with Lean when we worked on a summer project together with Sid. And this was like, this is when I realized how actually painful it is, and it's impossible to say Lean just like, okay, let Z be, like let lambda be a lattice in Euclidean space. So when I started on this, I did not realize that explaining Lean that this is a lattice in Euclidean space will take like several months of hard work and like several meetings every week and back and forth. And I think we did not actually work out from the first time. We had to, find a way how, like, what kind of dependent type will be good for this. And as a mathematician, for example, I should confess I'm not really educated on dependent types. So my mathematical education somehow went past that. So, so I think this is also a bit of a, but as I said, like if somebody does Lean, there is no way around. One has to learn that eventually. Yeah, and also like another here, like maybe frustration was that if we have, for example, I thought, okay, so once we define what a lattice is, and we define, for example, what is a Gram matrix, which is compute determinant of that Gram matrix, and we know what is the covolume of E8 lattice. But it turns out it's also not that simple, and again, like convincingly that this is this matrix, and it's like we can its determinant is actually computable, even though it might be defined as a real number, and we still know that it will be 1. So it. So things like this, I think they are difficult for newcomers. So, and so now after we, so this is what happens in the world of the Fourier transform. And here there is another, I think, interesting result, which would be very interesting to formalize on its own, which is this more general version of the Poisson summation formula. So again, we were able to do some preparatory work. So like so many things, they were already in the MathLib. For example, this lemma is already in the MathLib, and then then we would have to, we would need this this version of the Poisson summation formula to complete our proof of the Korn-Elkies-Gorbachev linear programming theorem. And so so again, like our somehow, like we need like, and actually if we want to have this like full strength of this LP bound, then we need both things. First we need the Poisson summation formula, and we also need this statement about periodic packings. And then we would be good with this theorem, which I think on itself it's also an interesting result. It's quite a nice and long paper. So it's and so another thing from the things that we need to be done are these contour integrals. And so here, of course, there are 2 ways one can go. One can just try to really formalize the Cauchy-Gurza theorem, which I think would be an extremely noble endeavor. At the same time, it's hard for me to say how much time and energy that would take. There is other ways to go, and I think they were already applied in some projects in analytic number theory, is that for some theorems we don't need like the full Cauchy-Gurza theorem for all possible curves. We need it for some particular contours when they're like straight lines or semicircles, which for me is, I don't know, it would be a bit of pity if we have to like forever keep doing this kind of patching. But yeah, this is the state of the art. Seems to be state of the art now, and so here this is what already exists in Lean, is this Cauchy-Gurza for rectangles, and so one thing that we have also, so here is Cauchy-Gurza for rectangles, And as we at some point we need to integrate over this half line, so we would also need Cauchy-Gourzat theorem over, to say, infinite rectangle-like shapes. And so this was one version of the theorem formalized by Sideb and Barvik. So they did it for this like kind of infinite rectangle, if I might say, or this type like rectangular form, given that our function f behaves nicely at in infinity. And but unfortunately, this is not enough for us. And for my application, we would need, it would be sufficient if we had integrals over rectangles and arcs of circles. And it has to do with, so what we kind of effectively would help us is a theorem like this. So if we could have a theorem for a contour like this, then we could somehow manufacture our preferred version of Cauchy-Gourzat theorem. And so maybe like, let me tell a few words like where those arcs of circles are coming from. They are coming from the action of the modular group. And it comes from the fact that if you take a line on the upper half plane and apply a linear fractional transformation to it, it might stay as a like linear segment, or it can actually turn into an arc. So this is where arcs are coming from. And so also one thing that we needed, it was all this like facts on modular forms. And so this is something Christopher was mainly working on. And so for the modular forms, we already had many things that already existed in MATLib. So Christopher, he had to somehow just connect our project to those existing things in the MATLib. But then several things had to be introduced. And maybe the most important one, which has interest outside of our project, would be the dimension formulas. So Christopher, he proved dimension formulas for all modular forms of level 1 and even weight. And so at some point we thought that we might also need dimension formulas for level 2, but fortunately we did not. We found some tricks how to overcome them. And then also in the middle of my informal mathematical talk, I showed you all this zoo of modular forms, different kind of functions. So we also needed to define them and prove their properties. So Christopher defined eta function, Ramanujan delta function, Eisenstein series E2, or the quasi-modular Eisenstein series. We would have to prove their transformation properties, and also what is important for our project, being able to compute Q expansions around different cusps and do it sufficiently pain-free. And yeah, so this here we like listed maybe a number of things which are not in the MATLib yet, but would be interesting to have. Probably would be needed by people who are doing modular forms and also want to do bin. So things like valence formulas, or more dimension formulas, and it would be really great to have some efficient way to do computations, for example, computations of Q expansions, and then maybe some more advanced things. And so, okay, so this is somehow the construction of the magic function, how it goes. So, yeah, so this is now everything has been, so the statements have been formalized in, so black means that they're now stated, but not proven yet. And so, yeah, so here somehow like here, this is the, to prove, for example, this part here, this is where we will need the Cauchy-Gourzat theorem, and also probably like this is still a minimalistic version of the nodes. Maybe as we are going over formalization, maybe each of these nodes have to be actually split into many more nodes to prove more. Like for example, like this, like what is one node here and one node here. It's an essentially it's a box for several conditions that have to be verified. And so this is now the proof of the inequalities. And so this is how I did inequalities in my original paper. So these are the two functions. I need to prove that they have certain satisfy. So this one is negative and this one is positive on an on this interval from 0 to infinity. And so original approach was rather like brutal force. So now there are actually two papers that give like analytic results for that. And so Siwu, he works with us on this project. So we are formalizing his algebraic proof of the inequality switch. And so another thing that became developed as a part of this project is a new library to work with complex numbers. And again, like this is something which before when I first learned about it, I did not realize that this is something which is difficult to do in Lean. For example, if we have an expression like this, it is in fact not that simple to prove it. So one has to cannot just state it. One really has to still search for a proof of it, and of course maybe doing it once is okay, but then if paper is more computation dependent and doing this 100 times would not be very feasible. So things like this, I think, at least for those who work in number theory or this type of number theory I'm working on, so being able to do such computations fast would be a big help. And so, so here is what now Sid, Heather, and have done. They have now deployed this new tactic, which is called normnum I, and now it can handle the computations with complex numbers more efficiently. So here are some examples, and maybe if we still have time for the discussion, then maybe Sid would be able to answer more about this this tactic and how to use it, how it is more powerful than what existed before. So here are also some examples on how things can. Example of things which are easier to do now with the new tactic. Yeah, and so now today we can actually open this project to more contributors, people who want to somehow turn all these white nodes into green. And so yes, so now what we have more or less 4 areas of working in. So work on general sphere packing, things like formalizing statement about periodic packings, formalizing statements about Poisson summation, then the modular forms, contour integration, and the work of the proof of inequalities on implementing the proof of Siwu. So each of these areas would have a reviewer who will review the pullbacks, and I think we agreed that for packings this would be Sid, right? And for modular forms this would be Christopher, and for contour integration, maybe we still need a volunteer for contour integration. And for inequalities, probably the Siwu would be the best possible person, because this is his proof and he knows it really, really well. And so, yeah, so this is, please join our project.
Okay, questions for Maryna?
Yes.
What Fourier analytic results do you need?
Sorry?
What kind of Fourier analytic results do you need?
Which results, sorry?
Like Fourier analysis.
Yeah, so this okay, so okay, yes, so like the main thing we need is so the main thing we need is somehow to work the Poisson to make the Poisson summation formula work. So like in this, so now it already exists in one lib, but only for like one-dimensional, and the possible lattice is Z. But we would need it for any dimension D and any arbitrary lattice lambda. So Actually, right now we have ideas on how to make it work. We have a bit of a like strategy, but yeah.
Okay.
More questions? Yeah.
Are you seeing any connection with Monstrous Moonshine and the work of EPFL?
Not really. I mean, I know that they exist, but that's maybe like not explicitly. I think in my work, somehow Monstrous Moonshine does not come up.
Kevin.
How far are you through? How long is there to go?
So this I don't know. Maybe it's like my experience with this type of project. So yeah, so this is our like tree, but then
Okay, well,
yeah. So like,
the question is, are there any bits which are going to be hell?
I don't. I mean, I think like yeah, some of the there is a lot of this like statements that we need. Maybe okay, maybe this could be. Maybe this part could be like not could become bigger eventually, but for example, like proving that something is Schwarz is that usually one has to check many conditions and as always to play around. Again, so you might think of your favorite proof from the analysis point of view, but then that one might be for some reason difficult to implement in Lean, and then you have search for different tactics. So yeah, then there are also like all this, of course. Yes, there are some more facts about modular forms that we need to prove. So then there are like many lemmas which look like, okay, so this is like my closed form. I take this modular form, which is a theta function multiplied by E2, and it has this Fourier expansion. So on one hand, it's not like it's not a very exciting theorem on its own, but then somebody still has to formalize it, and I don't know how easy it is to convince some people to formalize this type of not such an interesting. I think that there might be quite a few statements like that. So, for example, when you have to certify Fourier expansion of certain modular forms. But otherwise, yeah, there might be some surprises. So, like, I think I've already noticed all these like big things which might be interesting outside of our project. That we also need, like periodic packings, the Poisson summation formula, Cauchy-Gurza formula. So these are all things. I suppose they might be not that easy to get, but they also are things that could be interesting even outside of our project.
I mean, this is an advantage of the project existing, is that you're developing, you're forcing the community to develop mathematics which would be relevant elsewhere.
That's also the part which like the Sivou's algebraic proof. There also, I think he still has to prove some inequalities there. For example, he could have some modular form and to show that all of its Fourier coefficients are positive or non-negative. So questions like this, and to me it seems okay. It should be doable, but it also might be hell to prove it. So.
Are you aware how easy it would be in class that norm high tactic to generalize computation in arbitrary number fields? Like if you get given.
I don't know. Maybe there's something. Maybe you can come here also answer questions.
I can take this one. So there's been a lot of discussion about the capabilities of norm-i and how they can be extended. The truth is that the people. So it was Heather who ran a metaprogramming seminar at Imperial where Edison and I were both here. We kind of got introduced to this because of Heather. So we've been talking to other metaprogramming. This is our first time doing any sort of metaprogramming. It looks like it's going to be difficult but not impossible to apply similar procedures in sort of other number fields. We were talking about this a couple of days ago over dinner as well to try and not just number fields, but if you have any algebraic extension with some sort of polynomial relations, then maybe it might be possible to design a tactic where you give it some generators and relations, stuff like this, and can perform computations. We'll see where this goes. For now, I think, so we have a conv tactic called nomnami. We have a nomnam extension, and I think for now we're just going to PR this. Maybe with the help of other people here, we might be able to make it into a simproc as well. And with that, hopefully, we will have our bases covered for the complexes and worry about other things later.
Thank you very much.
Other questions?
I've got the whole story about contour integration? Have you formed an opinion whether it would be best to do that kind of in the framework of singular homology, or if you want to do it separately?
So this week I have not started that discussion that much. I think, yes, it's like because yeah, so maybe we have not discussed it yet with those who are experts in this area. But maybe it's a way, but probably it depends like how many things are already defined, and in a sense, like, I find it somehow, I don't know, aesthetically unpleasing to prove contour integration formulas for rectangles and circles, and not to do the real thing. It seems a bit wrong.
Apparently, we can't do triangles.
Yeah. So that somehow, I don't know. It feels wrong. So
But
yeah.
it's part,
Also,
it's part of the issue that you're having trouble even doing these, basic operations with complex numbers that's holding up contour integration.
I don't really. Well, okay, so of course, like if we decide to generalize this formula, maybe there are many different ways. Like how do we go? Do we go really through like single? I don't know. Maybe if somebody already formalized Stokes theorem, maybe it could be deduced from Stokes theorem or something like that. Maybe that would be like also an easy way to do it, because like of course, if you think about formalizing the proof of the formula I learned in my undergraduate class, where it was like this deformation of a contour, and yeah, that sounds like a nightmare. And even when I had to learn it, I thought that this is a bit right.
There is this issue, but even already deciding what is the statement we want to formalize has been discussed many times on this.
Yeah, so this is a bit of a problem, right? So you then okay, there's just, I think with discussions like this, if we want things to be moving, there should be we do it like this, maybe we do it wrong, but then we change it later.
Exactly. And we need, a project really needing it will make it much more likely to happen that when we were just filling in the undergrad curriculum but not agreeing on what should be the statement, then nothing was moving. But no, if we have this motivation, things will be moving.
Yeah, but I think even like the classical statement, it would be, I think it would unlock a lot of possibilities, like in analytic number theory, in classical complex analysis.
I may suspect that the classical statement is already not so well defined. What you mean by the classical statement?
Yes.
This is something you realize when you
So this is something when people need to make somehow. I don't know, I guess I'm not an analyst, I'm a number theorist, so for me I don't want it to be like the most general possible curve. It has to be, I don't know, like piecewise differentiable, piecewise smooth. I would be fine with it.
That's very good to know.
Yeah, but then, okay, there might be different schools of thoughts on it.
And also maybe a comment for people who are not really actively involved in all this, may be very surprised to learn that this stuff about norm I did not exist. But the thing is that by default, nothing exists until someone needs it, and then some people need to work. And so it's very good that every new project that reveals new holes like this is very valuable, and then people have to work on those tactics. And because nothing is magic in this story. So it's very good that this is good.
We are running over, and if it was anybody but Heather, I would say no. But Heather, why don't you give us the last question?
Oh, well, this is really just an addendum to the previous one, but I was going to say for your special domain with the square and the circle, and I were discussing this, and there is a trick for that.
Yes. She told me, there is a trick, but it also sounds like a bit like doing, complex analysis in the inverse direction, right?
I do understand the principle, but nonetheless, if that's the only contour you need,
Yeah. So this again, it's maybe so maybe for this project we can do it this way, but which probably would be somehow also some non-trivial amount of work. Yeah, so here I don't really know how to. I'm open to possibilities, but I also think that having somehow like more general statements where at least piecewise smooth contours are allowed, it would be quite amazing, and could be useful in many other projects in a similar area, not only in my area, but in a similar area.
So I think it's the hallmark of a great workshop and a great talk that everybody's ready to get to work. But first, let's have some coffee. So let's thank Maryna.